Hey everybody. So I'm going to work through a problem that several people have asked me for versions of this problem. So this is a problem dealing with points and lines. So I've written over here the given information. We have a point I'm calling A, which is 5, -2, -5. And then we have two planes. I've just labeled them 1 and 2, which have a line of intersection. And we want to find the plane containing the line of intersection and this point. So I'm going to try to draw the situation so we can start working out a strategy for figuring it out. So I'm not going to draw the two planes. I don't think that they're going to be necessary to understanding what's happening, and they'll just make the drawing complicated. But let's say this line here is the line of intersection between those two planes. Well, and then we'll have another point. We'll have a point, that's our point A. I guess I'll just leave it as black for now. So here's A out here, okay? What we're trying to find is that there is a plane that contains both of them. Okay, so this is just a little sketch, right? It's neither of the planes, presumably it's neither of the planes of intersection. I suppose it'd be worth it to double check, but if you plug in the values for A in both these equations, they're not true. That would be a cruel trick question to have you go through all the work of finding it just to find it's one of the original planes. So we want to figure out an equation for this plane. So what do we need for the equation of a plane? Well, we need a point and we need a normal vector. We've got our point. So what we need now is a normal vector. And there's a couple ways we can come up with a normal vector. One would be if we had two more points in the plane, in which case you have a total of 3 points and you create two vectors between any two pairings of those points and use them to get your normal vector. We could do that. I'm going to do something slightly different. I'm going to recognize that there is a vector somewhat available to us. It'll take a little bit of work, but there's a vector. The direction vector for this line lies in the plane, right? If we were to put that vector into, put its terminal initial point on the line, and then its terminal point on that would also be on the line, that it would be sitting in the plane just like that line is in the plane. So whatever the direction vector for that line is has to be a vector in the plane. The other thing we'll do, then we'll look at, let's go back. We will find a point on this line. I'm going to call that point B. And then we'll use that point to create a second vector between that point on the line and the point we were given, right? So then we'll have our two vectors in the plane. And then with those two vectors in the plane, we can create a normal vector, right? So this vector here will be our normal vector, okay? So let's name a few more things. I'm going to name this vector V, and I'll name this vector here U, okay? So we've got a few things up there. We might need some more stuff as we go, but let's start working on this. I'm going to start by trying to find the vector V. So if you recall from a previous exercise, when we have a line of intersection, the direction vector is going to be perpendicular to the both normal vectors, the normal vector of each plane. In other words, its it's perpendicular to both those normal vectors. So if we take the cross product of those two normal vectors, we will get a candidate direction vector, right? Remember, direction vectors for lines are never unique, but they're more or less unique in terms of we'll get the right direction, we'll get some scaled copy of all of the possible direction vectors. So what I need to do is take the cross product. So I'm going to call n1 the direction vector for, the normal vector for the first plane, and we can read this right off the coefficients in the equation. So this normal vector is -3. This is kind of too big for me. I'm gonna go to the smaller pen. Sorry. We can just read the direction vector n1. Sorry, the normal vector n1 off of those coefficients: -3, 1, -3. n2 is going to be -7, -8. -2, and then V is going to be the cross product of these two. Okay, so I worked this out already. -26, 15, and 31. Okay, now let me say something about that cross product, since I just skipped over the computation. On the one hand, cross products are not hard. They're just multiplication and addition or subtraction. On the other hand, they are hard because there's a lot of different things and a lot of places to screw up. This is the second time I've prepared this problem already, and the first time I prepared it, I got it wrong because I dropped a negative sign in one of my cross products at one point, and it was actually at this point one of these I forget which component I multiplied wrong in my head. Anyways, I get that frustration. The way I fixed it was to work more largely and more carefully. But in any event, this is what we're going to call V. -26, 15, 31. Okay, so that's a piece of information I'm going to want later. I'm going to give it a nice little box so I don't have to sift through my work later and just hold on to that. Okay, so we've got one vector in the plane. Now I need the point B. Okay, so remember what point B is. B is some point on this line, and this line is the line of intersection of these two planes. In other words, B must be on both of these planes. Okay, now in my drawing it looks like I've picked some particular point of B. It's just any point on the line will do for this. So we're going to use, oops, I did not mean to do that. We're going to use an idea that we've used before, which is that because this line, right, now that we have the direction vector, notice none of its components are 0. That means the coordinates, the components being spit out by the vector equation of this line, or the coordinates being spit out by the parametric equation of this line, are linear equations with non-zero slopes. In other words, each coordinate will have some value of the parameter so that it goes through every single possible value of the coordinate, which means at some point there, oops, let's name this line L. There is a point on L1 with x coordinate 0. Okay, there's some point on that line that has an x coordinate 0, because whatever, pick any point on this line, at some point when we move in this direction, right, scaled versions of this direction, right, so if the point, you'll eventually get to 0, right, so you can scale by positive or negative, you can eventually get there. So how do we find this now? Well, this is, the points on this line are also points in both of these planes. So that means that point also has to satisfy both of these equations. So it has an x coordinate of 0 and it satisfies both of these equations, which means its y and z coordinates have to satisfy both of these. Okay? So we got to solve these two, this system of equations. There's two equations here. I think I've been doing elimination almost every time I solve systems. Let's do a substitution. This one's kind of nice oops, this is wrong. This should be not 0. This should be negative 30, pardon me. Okay, so if I just add the 3z to the other side, I get y equals 3z minus 30. Okay, and I can substitute that into this equation, so I get negative 8 times 3z minus 30 minus 2z equals 22. I get negative 24z plus 240 minus 2z equals 22. Negative 26z equals negative 218. Divide and reduce, so these are both divisible by 2. I'll get negative, oh, they're both going to be negative, so this will be a positive in the end. Let's see, we'll have positive 109 over 13. Okay, so I divided negative 218 by negative 26 and reduced that fraction to this. So there is our z coordinate. Our y coordinate we can get from here. So y, coming back up here, y is going to be 3 times 109 over 13 minus 30, or 327 over 13 minus 30 times 13 would be 390 over 13. So this is negative 63 over 13 equals y. So now we have the point B. Let's put that up here. B is equal, let's just write it this way. B is the point, 0, negative 63 over 13, 109 over 13. Okay, so my next step, right? So now I've got a point on the line. I need one more vector, and I have 2 points on the line because I have the point A and I have the point B. So let's make the vector u, just like how I drew it, it's going to be the vector from B to A, right? It could be either from A to B, B to A. I'm just going to stick with what I chose here. So we take the coordinates of A and subtract the coordinates of B. So I'll get 5, negative 2 minus negative 63 over 13 makes it a plus. And negative 5 minus 109 over 13. So what do we get? 5, negative 26 plus 63 is 37 over 13. And this one is going to be negative 65 minus 109 is negative 174 over 13. And there is our vector u. Okay, so far so good. We've got 2 vectors in the plane, several points, 2 points in the plane. We want this vector, this blue vector, let's name this one while I'm here. Let's call this just n with no subscript. This is the one we're looking for. So notice a couple things. So we're going to take a cross product, right? We're going to take, we can do v cross u or u cross v. I think I did v cross u. I did one little step first that you don't have to do. I just didn't feel like dealing with these fractions. So I took u and scaled it by 13. I called that new vector w, just multiplying into all the components, 65, 37, negative 174, right? You can decide if that's easier or not. I just didn't feel like dealing with the fractions. It means later we're going to have some factors of 13 floating around that I might want to divide out because my numbers will get pretty huge. But I really just didn't feel like writing over 13 over and over again, right? Notice why this makes sense. All I'm doing is changing the length of u, right? I'm just taking this vector, right, in the same direction and making it 13 times longer. It still sits in that plane. And so when we take the cross product, we're still going to get a perpendicular vector, a normal vector, right? It will be a different size, but it doesn't matter. Our normal vectors are not unique, just like our direction vectors are not unique. So that's what I chose to do. So now I took v cross w. Let's see what that looks like. Yeah, that's what I did. And so I'll spare you this massive computation. V has negative 26, 15, and 31 crossed with W. It worked out to be negative 3757, negative 2509, negative 1937. Okay, now that's pretty huge. The negatives are also annoying. So what I did was I took negative 1/13 of this vector, right? So I remembered that I had multiplied this vector by 13, so I knew there were factors of 13 floating around in my computation everywhere. So I didn't really work hard to I didn't have some magic insight or notice that these are all divisible by 13. I just knew that every component here had a 13 in it when I was multiplying and combining. So there was going to be factors of 13 here. So I'm dividing by 13, and I multiplied by negative to get rid of the negative. Remember, that's equivalent. It doesn't matter if our normal vector is how long it is, or we can even have it pointing straight down. That would still work, right? So there's nothing unique about that in terms of scaling it. We can scale these however we want. I just did it to make it convenient. And when you do this, you just divide each of these by negative 13. I got 289, 193, 149. Okay? You didn't have to do that. You could have used this normal vector. It's just an uglier looking equation at the end. You didn't have to scale u by 13, and I never would have had to unscale it. I just thought that was simpler than dealing with fractions. In any event, this is the vector n. Okay? So now we're on our last step. We have all the pieces we need. So let me clear some space so we can do this last part. So what do I need to be able to see? I guess all I need is the vector n for this last step. So I'm just going to, I'm going to save all of this. And then let's get rid of everything else. All right, let's just take n over to here. So there's the vector n. There's the vector n, and we already have this point. So now the equation of the vector, remember what we do for the vector equation of, sorry, not the equation of the vector, that makes no sense. The vector equation of the plane, we take r minus r naught, right? Where r minus r naught is, vector r is just going to be some arbitrary point in our plane. R naught is a vector pointing at a point in our plane. I'll choose the point A, so r naught is pointing at that point. So then this looks like n dot x minus 5, y plus 2, z plus 5 is equal to 0. If we compute this dot product, it's going to look like 289 x minus 5 plus 193 y plus 2 plus 149 z plus 5 is equal to 0, right? And this is a perfectly acceptable equation of a plane. You could also you could expand these things and write this as 193y plus 149z minus 314, I believe is what I got. It's equal to 0. Some people put the 314 on the other side. It doesn't really matter. And that is the equation of the plane containing the line of intersection and that point we were given. So a couple of things. We're going to take a look at that with a grapher in just a second. I do want to point out a couple of stops along the way. I just went straight through this solution, right? Once I did this once and made an error, I was 10 times more careful the second time. And I just want to point out some things that I did. For instance, when I computed a point in the plane, point B, I took that value and I put it into my plane equations on a piece of scratch paper to make sure I had gotten a point correctly, right? That I didn't have some minor error in computation. I think conceptually all of this is doable, but sometimes it's easy to make little errors. So I plugged it into my plane equations to see that it was a point on that plane, right? So that's the kind of quick check that we can do, right? Every time I created a cross product, I double checked that it was perpendicular to both of the vectors that I wanted it to be perpendicular to, so that by taking a dot product and seeing that it was 0, right? So another place where it's easy to make an error, you can do a quick check. That should tell you if you're wrong. The only way it won't is if you somehow make kind of the same error in reverse so that you think that you've actually done it correctly. Anyways, that's just advice for this kind of problem that sort of, it really just has a bunch of little steps in a row. I think of it like trying to multiply two 15-digit numbers together by hand. We could all do that. We just have to be really careful. There's a ton of opportunities along the way to screw that up. Okay, let's move from this over to a nicer picture. So let me share with you. Okay, so I think I named everything the same here. Oops, I didn't mean to do that. So what I've got here is that point A, that was the given point that we wanted to contain. And then here are our two original planes that were given. So see, A is not on those planes. And I'm just going to remove our axes. I don't think we need to really know where these things are in relation to the axes. So we can see equation 1 and equation 2 are just these planes. We can see that line of intersection. Let's make it a little clearer. There's the line of intersection, right? And we want to find a plane that contains that line and that point A. So let's go through our process and see what we did. I'm going to take the plane. Well, let's do one more step and then I'll take that plane away. Here's V, the direction vector of this line. Zoom out a little bit, right? So we see that vector sits in both of those planes. And eventually we're going to want it sitting in the plane that we're going to construct. All right, I'm going to pull the two original planes away. So now, once we have this direction vector and our point, oh, sorry, one more thing before I take these away. Then we found the point B, which is a point sitting in both planes, right? So I put the vector V at B just to make this drawing or this representation convenient. V can really be sitting anywhere, but that point B is on our line and it's in both planes, right? So that was a key, that was the key features of that point B. All right, so now I'm going to remove the plane. So now we've got our line, we've got 2 points and the direction vector of that line. We then created the vector U between A and B, right? So this is the point A out here, this is the point B in here, and there's that vector U between them, okay? Sorry, sometimes I gotta just reset, zoom to fit, there we go. Okay, so now, what was the next thing we did? Well, I did this thing of creating the vector W, which was a scaled version of U. So now I've got that. Notice it's just in the same direction, just sticking out 13 times farther, right? So that was just something I did because I thought it made computation a little bit nicer. Then we took their cross product to get the vector N. There's N. Let me make this zoom a little nicer. So we can kind of see, I think, that N is perpendicular to both of them, right? If we look around at these different angles, once we put the plane in there, it'll be a bit easier to see. Well, we've got our normal vector, we had our point, we can then create the plane, and there is the plane, right? See that both vectors are sitting in that plane. When we look at it at the side, they're right there, and that vector N is shooting right out of it, okay? So that was the geometry of the whole situation. If I put those original planes back in, I don't know if we learn anything, it just gets more complicated. At this zoom, it looks like they're all, let's zoom, let's go back to, Oh, yeah, it's just kind of a mess when there's this many things. But hopefully this helps seeing this one, I think, where we've got those two vectors living in that plane. Let me zoom to fit one more time. And this normal vector sitting out of it. And that was the equation we came up with. Okay, that is it for this one. Thanks, everybody. I will see you next time.